Alright, so I want to talk about two new concepts in chapter 16, and that's electrical energy and this new term we're going to refer to as potential difference. So in 120 we were concerned with energy, right? Once we did Newton's laws and kinematics and all that stuff, we were concerned about the energy model and how energy is transformed in a system, or how energy is transferred into or out of a system, right? So we talked about work and kinetic energy, potential energy, all that stuff. So we're dealing with charged particles that are exerting forces on each other. Now, up to this point, our charges have been stationary, right? Maybe in your WebAssign problems you've had to find the acceleration of a particle if you found the net force or something like that. But a lot of our examples, we've just been looking at the forces charged particles exert on each other, and then the fields that they produce, the electric fields. But in reality, if you have a charged particle that's undergoing a force due to another particle, its energy is changing, right? It's going to undergo a displacement, and that means that other agent that's doing or that's applying a force is doing work, right? And this is a slide from 120, so we're going to go back to a couple 120 concepts just as a review, and then we'll talk about energy in terms of moving particles, right? Interacting particles. So the definition of work was the dot product of the force vector on an object and its displacement vector. Okay, and I'll upload the old 120 slides from last semester. So if there's anybody who took it earlier, maybe last year, or took it with another school, I'll put my slides up for 120 in this content tab for chapter 16. So basically, work is the transfer of energy into a system. Right, these are units of Newton meters. We call that a joule. So if there's any external agent doing work on a system, then energy is being transferred either into or out of the system, okay, depending on whether the work is positive or negative. So how do we determine whether work is positive or negative? We have to look at the direction that the force and the displacement vectors are pointing, right? So the dot product is the magnitude of the two vectors times the cosine of the angle between them. We see that work will be negative if the angle between the force vector and the displacement vector are 180, right? If the angle is 180 degrees, then the cosine of 180 is -1. And then there's another range of angles, right? There's a range of angles where you'll get a negative sign for this expression here, right? So if there's any component of the force vector that's pointing in the opposite direction of the displacement vector, then the work is negative. And so we'll talk about what that means in terms of a charged particle in a field and its motion, and how we determine those negative signs fairly quickly, right? We don't want to have to do the dot product every time, so we're gonna develop some formulas, do a couple problems, and then we'll look and see how work changes the system. So what I want to do is I want to go back to my gravity analogy. We talked about in chapter 15, we talked about Newton's law of gravitation and how that's a pair of forces between two massive particles that are interacting, and it's a long-range force, right? And so we saw the similarities between Coulomb's law and Newton's law of gravitation. So I want to go back to the first example of potential energy, and that was gravitational potential energy, right? And our first example was an object that is some height above the surface of the Earth, right? We're close to the surface of the Earth, but we're above the surface of the Earth. So if you have the object and it's originally on the surface of the Earth, we say that its potential energy is 0, right? It's not going to fall any farther. We pick that to be our 0 potential energy configuration. And if you were with me last semester, we talked about two people, Amber and Bill. I like to be an Amber because she always picked the surface of the Earth, or the lowest point an object could reach, as the 0 potential. So what happens? You are not part of the system. You're an external agent, right? So let's say the ball is the system. You lift the ball up, right? You apply a force in the positive y direction. The object's displacement is in the positive y direction. So you're doing positive work, right? You're doing positive work as an external agent on that ball. Simultaneously, the Earth is applying a force in the negative y direction, but the object's displacement is still the positive y direction. So the Earth, while you're doing positive work, the Earth is doing negative work. Okay? And what we did was to introduce the idea of conservation of energy. We included the Earth and the object as our system. Right? We included the Earth object system. We redefined our system so we could look to see how energy was transformed in the system, rather than treating Earth as the external agent. And we're going to do something similar when we talk about electric potential energy, right, and work done on a charge. So what I did here was I took Newton's law of universal gravitation and I substituted that in for mg, for the gravitational force. And I did a little simplification here just because this is an algebra-based course, so I kind of cheated here a little bit and simplified so we could avoid, calculus. So what I did was I took the height h that this object was, right, and I put it a sufficient distance away, right? So I'm accounting for the range of distances from the surface of the Earth to include, the moon and other planets, like really, really large distances. And so in doing this, I'm simplifying and I'm making the radius of the Earth, because this is actually the center of the Earth, I'm kind of making the radius of the Earth negligible, right? So I'm making h so large to encompass, all different types of scenarios, okay? So basically the distance between the surface of the Earth and the object could be the same as the distance between the center of the Earth and the object. And so I'm kind of simplifying and I'm just saying let that h be the distance between the two objects, right? Rather than like a little tiny object close to the surface of the Earth. And so I'm basically canceling out one h term with one r term here. And there's a potential energy expression. And if you notice, it's proportional to the distance between the two objects now, right? If we go back to our Earth-Moon scenario, it's inversely proportional to the distance between the two objects. Notice it's not an r squared anymore. But it's still proportional to the mass of the two objects, right? So the more massive the objects are, the more gravitational potential energy the system has, right? And the farther they are, the smaller the gravitational potential energy is. Okay. Now if you notice in this expression, when is the potential energy of the system approaching 0? Not technically 0, but approaching 0. As r approaches infinity, this potential energy term will go to 0. Okay, so the farther away the planets are, the closer the potential energy of the system gets to 0. Okay, so this is our potential energy term for two interacting massive bodies that are separated by some distance. So we haven't dealt with a uniform electric field yet because we've always been dealing with point charges. So chapter 15 dealt with point charges. Now I'm going to deal with a uniform electric field, okay, and we're going to do something like this in lab in a couple weeks. So what I did was I took a bunch of point charges and I set them up in a line, right, in just a 2D line for now, okay. What actually happens for this object, this is actually a plate. This would be a metal plate that's positively charged. But we'll be working in 2 dimensions, okay, so this is a line of charge, right, line of positive charge, and then on the other side there's a line of negative charge, okay. So we'll see later on that in order to do this we can connect this to a battery or something. Sorry about that. We connect that to a connect this to a battery, and then we have positively charged particles on one side, negatively charged particles on one side. So we know from the definition of electric field that it's always going to be pointing from the positive charge and to the negative charge. So what we did here by lining up these charges parallel to one another, we've created a uniform electric field that's in a straight line. We know that the electric field gets weaker as it gets farther away from the positive charge, but it also gets stronger in this direction due to the negative charge. So if we have two oppositely charged plates sufficiently close to one another, we have a uniform electric field, right? So this electric field is constant. It's not like kq over r squared anymore. It's uniform, it's constant, it's the same strength throughout. So what we do is I'm gonna take a particle from infinity, right? I'm all the way over here. I'm hundreds and hundreds and hundreds of meters away, right? And picture me taking this positive charge, right? The single positive charge, and I push it to the left from all the way hundreds and hundreds and hundreds of meters away, and I put it here. Okay, so I just did work on this system. Okay, the charge plate system, I just did work. Okay, so I moved it a displacement, right, in the negative x direction. I applied a force in the negative x direction, so I did positive work. So this system now has more energy than it did because of the work that I did. I'm the external agent, and I decided that I would put this charge in between the plates. So I did positive work. All right. Now what happens is I've got a system, right? I leave the system. I'm no longer interacting with it. Now I've got a system that has some energy in it. What type of energy does this system have right now? It's got potential energy. Because when I let go of this charge, what is it going to do? It's going to go in that direction. Okay, it's going to go in that direction. And then eventually it's going to hit this plate. Right? It's going to hit this plate. Maybe it'll combine with a negative charge and become neutral or something. Right? We don't know what's going to happen yet. But it's going to move towards this plate, and it's going to have some kinetic energy. But if it's at rest here, it's got to start with some sort of potential energy, some sort of energy that's transformed into kinetic energy. And how is that energy being transformed? That's due to the force that it's experiencing with this electric field. So I can derive an expression for the work that these two plates are doing on this charge. Okay, so this is after I let go of it. I'm no longer part of the system. Okay, so this particle is going to travel from x initial to x final. Right? The electric field is going to push a positive charge in the positive x direction. Alright, so my displacement is positive. Right? It's pointing in the positive x direction. The electric field is also pointing in the positive x direction. So what I did was I took my expression for the electric force in terms of the E field, and I substituted that in to my dot product formula. Okay, so F dot R is now QE dot delta X. Right, so it's the force experienced by the particle due to the electric field times its displacement. Now in this diagram, those vectors are pointing in the same direction. The angle between them is 0. Cosine of 0 is 1. So I have positive work in this case. Okay, QE delta X. My charge is positive. The electric field is pointing in the positive X direction, and the displacement is in the positive X direction. Okay. Now all three signs of these quantities matter. Okay. If this was a negatively charged particle, I'd have to put a negative sign there. If either the E field or the displacement were in the negative X direction, I'd have to put negative signs in there. Okay. So even though work is a scalar, it can be positive or negative depending on the charge and the direction of the electric field. So I've got this expression for work. we know from 120 that work is the change in kinetic energy, right? So this expression for work I can use to find the change in kinetic energy. Also from 120, okay, if you go back to our Earth object scenario, right, the Earth was doing negative work on the object as I lifted it up. But if the Earth is part of the system, the work is the negative change in potential. Okay, so this is from 120. That's how work changes the potential energy. That's how work changes the kinetic energy. Right? In an isolated system, I can set these two equal to each other. Right? Delta K equals negative delta U. If I added delta U to both sides, I'd get delta K plus delta U equals 0, which is my law of conservation of energy. So I'm taking these concepts of energy and I'm transferring them to this system of electric charges. So this is my expression for the work done on a particle in a uniform field, uniform electric field. If I want to find something about its kinetic energy, I can set this equal to delta Ke. If I wanted to find something about how the potential changes, I can set it equal to negative that term. Okay. So we'll talk about these two scenarios, right? I've already done work on the system, right? I already put the charge in between the plates, and I want to see what happens with different particles once I let go of them and I let the system transform the energy. Okay, so I take a positive charge and I put it close to the positive plate. It initially has some electric potential energy, right? When you let go of the charge, it's going to go in the direction, right? It's going to go in the direction of the electric field. Its potential energy is going to be transferred to kinetic energy. Okay, so potential energy is going to decrease and kinetic energy is going to increase. Okay, so if I look back here, the charge is positive, the electric field is in the negative x direction, but the displacement is also in the negative x direction. So the plates are doing positive work, right? The plates are doing positive work on the charge. Okay. If I were to take a negative charge and I put it towards the negative plate, it's going to travel towards the positive plate, but its potential energy is still going to decrease and its kinetic energy is going to increase, just like this charge up here, but it's traveling in a different direction. It's traveling opposite the electric field. So if I go back to this expression, I've got a negative charge. My electric field is still in the negative x direction, but my displacement is in the positive x direction. So I've got a negative times a positive. I'm still left with the plates doing positive work on the charge. Right? So in both of these scenarios, the plates are doing positive work. But again, the plates are part of the system, so the initial potential energy the charge had is transferred to kinetic energy once it moves a certain displacement. Okay, so the plates are always going to do positive work on the charge because it's going to travel based on the direction of the electric field. It's going to be attracted to, the oppositely charged plates. But again, just like our object Earth system, we're going to say this is an isolated system, so the total mechanical energy is going to be conserved. Potential is going to be transformed into kinetic energy. So what do I want? I got work, I've got potential energy, I could find kinetic energy. Just like I did with gravity, I have an expression. Right, I have an expression for the potential energy of a two-particle system. What if the moon was gone? Right, we're going to do the same thing we did with electric field, just with potential energy. What if the moon was gone and we only had the Earth? Is there still a potential energy field? Meaning, is there an amount of potential energy per unit mass at some location? right? If I put a 1 kilogram object at some location, what would the potential energy of the system be? And so I took this potential energy term and I divided it by the mass of the moon. I'm taking the moon out of the system, now it's just the Earth. Okay. So we see the potential energy per unit mass in our old 120 terms when we were just talking about gravity as mg, it's just gh. Okay. And that's joules per kilogram. Right? That's joules per unit kilogram. Meters per second squared times meters, that's meters squared per second squared. Right? So a joule is a kilogram meter squared per second squared. This is units of joules per kilogram. Energy per unit mass. Now if I took Newton's law of universal gravitation, and this potential energy term I derived from that, if I divide that by the mass of the moon, I get this expression here. Which again, just like with the force field, right, my gravitational field, it only depends upon the mass of the Earth. So this is also joules per kilogram, but notice it's not dependent upon the other planet, right, or the moon, the satellite that I took out of the system. So even though the moon is not there, there's still a potential energy field. What would the potential energy of the system be if I put the moon back there? Okay. So what does that mean? What if I don't have a charge in between the plates? Is there still a potential energy field? The answer is yes. What potential would a 1 Coulomb charge have if I put it somewhere between the plates? Okay. So it's purely visual conceptual field. I don't actually see charges moving. I don't see, you know, a massive body being attracted to another body, but there is still an electric potential energy field there. Okay. And so what I want is I want to do the same thing for electric potential energy. Right? So I've got this expression for my electric potential energy of a charge that's moving in that field. But what if that charge wasn't moving? Or what if that charge wasn't there? So I want a potential energy value per unit charge. Right? Just like I want a force per unit charge for an electric field, I want a potential energy field. So I want the potential energy per unit charge in between these two plates. So I take my new expression for electric potential energy in a uniform field, negative QE delta X, divide it by the charge, and I've got an expression for the potential energy field. For a potential energy field. Okay, this is in joules per coulomb. Right, our gravitational potential energy field was joules per kilogram. This is joules per coulomb. Okay, so I don't have a charge in between the plates, but I do have a potential energy field. And so what is this thing right here? Right, I want to define this as something. Right, what's my potential energy field? Right, my potential energy field. So this charge would be in a uniform field. It would be going through some delta X. It would be moving. Okay, so I'm not looking at the potential energy at some point. I'm looking at the potential energy per unit charge along some distance. Okay, so that's a change in potential energy per unit charge. I've got this delta U, I've got this delta X, so it's a change in potential energy per unit charge. And so we call that potential difference. We call that a difference in potential. Okay, very similar to the term electric potential energy. This can be very confusing. Okay, delta U is electric potential energy. Your book uses PE. Sorry, it's an old habit of mine. You know, I like a lot of textbooks that use capital U for potential energy. Okay, so if you ever see me use a U, I just mean PE. So this is my potential energy change of an object that moves, but I want the change in electric potential between 2 points. Even though there's not a charge there, there's a change in electric potential. There's a change in the electric potential energy field. Okay? So I'm getting tired of saying potential, energy, field, difference, right? All these terms are getting really, really confusing. So for chapters 18 and beyond, I want to use a different term, so why not just start right now? I want to use the word voltage, okay? So when I talk about electric potential, I'm talking about a change in electric potential energy per unit charge. But to help us eliminate confusion between these two terms, I'm going to call it voltage. Okay? So the SI unit for 1 volt, now this can be confusing too, right? The variable for potential difference is V, but the units are also V, okay? Named after Alessandro Volta. I believe his first name was Alessandro, okay? So the SI unit is the volt. The variable name, or the quantity name, we call voltage, which also means electric potential. So I'll be using delta V, and I'll be using voltage from now on to try to eliminate that confusion. So that's a joule per coulomb, okay? Potential energy per unit charge. So a volt is a joule per coulomb, okay? So that's potential difference. Now if I take this is an important property, an important relationship between electric field and voltage. If I divide both sides by delta x here, by negative delta x, excuse me, I get the magnitude of the electric field is equal to the negative change in potential with respect to position. Okay, so it's a change in voltage with respect to position. So what does this mean? This means that the voltage, or the potential difference, decreases in the direction of an electric field. So let me go back to one of these diagrams. Okay, from this location to this location, if I've got a positive charge moving from right to left, this particle is traveling in the direction of the electric field. Its potential energy is decreasing. The voltage along this displacement in the negative x direction, is decreasing. Okay, the E field is pointing in the negative x direction. The voltage is decreasing in the negative x direction. Okay, so that's the relationship. And all you calculus gurus out there, you can see that if I had a voltage function that wasn't constant, right? If this wasn't a constant voltage, this would be a derivative, right? This would be a first derivative. So E is negative dV over dx. So I won't give you any non-constant or non-linear voltage functions in this class, but just something to kind of help you visualize it if you've seen calculus before. So the electric field is the negative change in potential or voltage with respect to position. So we see that these units of electric field are volts per meter. So a Newton per coulomb is also a volt per meter, right? And so in your spare time you can set newtons per coulomb equal to volts per meter, and then, you know, write them in their respective SI units and simplify it and see that it's true. Okay, so a volt per meter is also a Newton per coulomb. Alright, so basically what we're doing here is we're creating what's called a parallel plate capacitor. Okay, so a capacitor stores energy in an electric field. Okay, and what we can do is we can set it up in a circuit, and we can charge it, and we can flip switches. We can basically store electric energy for a finite period of time in a capacitor, and then we can release it, and then it can do work somewhere else in the circuit. So in this case, right, we've dealt with this scenario, right, these slides right here. Okay, we've got a positively charged plate on the right side now. Now this will happen, right? Your WebAssign, you'll have the positively charged plate on the left side, negatively charged plate on the right side. They'll be switched, right? A particle will start from a different position. So for now, we'll just deal with the vectors, right? It's going to be in 1D. The E field could be pointing in the positive or negative x direction. The displacement of the charge could be positive, negative x direction. So just watch out for that. Keep your signs straight. All the signs matter. The sign of the charge, direction of the E field, direction of the charge's displacement, all that stuff matters. So we got to be careful with our signs. So we'll do this in lab. We'll draw some diagrams up, and this will be helpful for our practice problems. So I have a positively charged plate here, and I've got a negatively charged plate here. So what I did was I set it up, or I hooked these two plates up to a 1.5 volt battery, say. Right. We'll talk more about batteries when we get farther on in chapters 17 and 18. So I hook it up to a battery. I've got a high potential here, right? I got a bunch of positive charge here, negative charge here. The voltage across the two plates is 1.5 volts. 1.5 volts. So that's the potential difference. That's delta V. That's V final minus V initial. If I took V final to be here and V initial to be here, I'd have a potential difference of negative 1.5 volts. Okay. Generally, our voltages are positive between the two plates. We pick our convention to where V final is the high potential, V initial is the low potential. Okay. So generally, the voltage across two plates is going to be positive. So we see the electric field is pointing in the negative x direction, away from the positive charge towards the negative charge. And then these green dotted lines, they run perpendicular to the electric field. So these are basically the steps, right? This shows me how the voltage is decreasing, right? My voltage is stepping down from 1.5 volts down to 0 volts. So these voltage lines, right, which will be called later as equipotential contours or equipotential lines, they always run perpendicular to the electric field, right? Because voltage decreases in the direction of an electric field. Okay, so right here the electric field points in the direction of decreasing potential. All right, that's what this means. So as voltage goes from high to low, that's the direction of the electric field. That's the direction a positively charged particle would travel if it was only under the influence of the electric field. So let's do a couple examples. My first one is an electron. So it's in a uniform electric field. So it's in between two plates of a capacitor, and the electric field is pointing in the negative x direction, and it's a uniform strength of 400 newtons per coulomb. So I have the magnitude of the electric field and I have the direction. So this is going to give me some hint as to how to draw my diagram. Right? I suggest you, anytime you get a situation like this, draw the plates so that the electric field corresponds and it's got the right direction. Okay, so what I'm going to do here is I'm going to draw a positive plate on the right side and a negative plate on the left side, right? Because the E field goes from positive to negative. So I'm going to draw a positive plate on the right side, negative plate on the left side. Okay, so there's the direction of my electric field. Sometimes you'll be asked to draw the field in between the plates. I'm just going to draw it down here so I don't mess my diagram up. So it says there's an electron that's initially at rest. Right? Initially at rest means V initial is 0. That also means the initial kinetic energy of the electron is 0. So it tells me after the electron has moved 5.2 centimeters in the positive x direction. So I know that the initial position is going to be, say, x equals 0. The final position is going to be x equals positive 5.2 centimeters. Now I'm looking at this situation before I deal with any numbers or algebra or anything like that. I want to ask myself if the situation makes sense. Okay. This is an isolated system. I'm assuming that there aren't any external agents. The second example we'll deal with the opposite. Okay? But the only thing that's doing work on this charge is the plates. So this is an isolated system. And this is naturally how the charge would move. It's a negatively charged particle. It would move away from the negative plate and towards the positive plate. So I'm going to say this is an isolated system and energy is conserved. Okay. So I'm going to calculate the work done. The first thing they want me to do is calculate the work done on the electron. So the electric field is in the negative x direction. I have a value for that. The displacement is in the positive x direction. It's an electron, so it's got a negative charge. Okay, so my E field is negative, my displacement is positive, my charge is negative. So I plug these values in, right? Because here's what's going to happen. I'm not dealing with the cosine of theta right now because either the system, the electric field is opposite the displacement or the electric field is in the same direction. Okay. So in this case I see that the electric field is in the opposite direction of the displacement, but my charge is negative. Okay. So I've got a negative sign, a positive sign, so I expect positive work to be done on the particle by the plates, which again is making sense, right? Isolated system, the charges are doing positive work. Kinetic energy is going to increase while potential energy decreases. Okay, and that's what's happening. It's starting from rest, it has an initial electric potential, and then it's got a final kinetic at some point later. Okay, so the total work done is a very small amount of work, right? It's a strong E field, but it's a very, very small charged particle, right? It's a single electron. So the work done is 3.3 times 10 to the negative 18 joules. Positive work, potential energy decreases, kinetic energy increases. Part B, find the speed of the electron after the displacement. So I set the work equal to the change in kinetic energy, but the particle's initially at rest. So K initial is 0. So the work is just equal to the final kinetic. So I know what the work is. I know what the mass of an electron is. It was a while ago, but I can look it up. It's 9.11 times 10 to the negative 31 kilograms. Keep that handy. So I can solve this for the final velocity. Multiply both sides by 2, divide both sides by the mass, take the square root of both sides. I've got a nice expression for the final velocity of the particle in terms of quantities I know. So I can substitute my value in for the work, substitute the mass in. Don't forget to take the square root. I forget that. 2.7 times 10 to the 6 meters per second. Very, very fast. Okay, it doesn't take a whole lot of force. It doesn't take a whole lot of work on such a small particle, right? A particle with such a low mass. You notice this denominator is much smaller, right? So I've got a very, very high speed for this electron. What is the potential difference through which the electron moves? So anytime I see the word potential difference, I have to remind myself that we're talking about voltage. Okay, we're not talking about a change in potential energy or anything like that. We're talking about voltage, so I'm looking for a delta V. Now in this scenario, I can do this one of two ways. So I know that voltage is potential energy per unit charge, and I know that the change of potential energy is equal to the negative work done. So I can use this expression for change in potential, change in voltage, is delta U over Q, which is negative W over Q. I know the work, I know the charge of the electron, and I get a potential difference or a voltage of 20.6 volts. Okay. So that means it's moving. Let's go back to my picture here, right? It's moving opposite the direction of the electric field, so it's moving from a low potential to a high potential. So the potential difference across that delta X is positive, which makes sense, right? It's a negatively charged particle moving to a higher potential. Even though the particle's potential energy is decreasing, the potential field or the voltage field is independent of that charge. Right? So this is the tricky part. I'm not talking about the charge in particular. I'm just talking about the voltage, the change in voltage, the change in electric potential, the potential difference between those two locations. Okay, so I'm going from a high potential to a low potential. Even though the object's potential energy is decreasing, it's moving from a low potential to a high potential. Another way I could do this is use my other expression, right? Negative E delta X for my voltage. Okay, this negative sign, don't forget that. All right, so I've got a negative E field, I've got a positive displacement for the charge. Notice it doesn't depend on the magnitude of the charge in this expression. So I had a little rounding issue with with my quantities. I think I got closer to 20.8 or something like that. But I got a very, very similar change in potential, which was also positive. Right? So using both of these expressions, I get a positive change in potential, meaning the particle is moving from a low potential position to a high potential position. Okay. Again, even though the potential energy of the particle is decreasing, it's moving from a low potential to a high potential. So for practice, do this. Do the same setup, right? Same electric field, except replace the electron with a proton. Put the proton right here at X final, closer to the positive plate. That means you're going to change the sign of the charge. That's going to be a positive Q. And then you're going to change the sign of the displacement, because what's going to happen if I put a positive charge here, it's going to move away from the positive charge, or from the positive plate towards the negative plate. Okay, so the displacement, the sign of the displacement is going to change, but the sign of the charge is also going to change. Okay, make it a proton. The mass of the proton will also change, so look up the mass of the proton. Go through this problem just with the proton, starting here at X final, ending over here at X initial. So change the displacement sign, change the charge sign, change the mass to the mass of a proton, and you'll see a lot of similarities. Right? You'll see a lot of similarities between the work done and then the change in potential. What will change is the kinetic energy, right? Because you got a much more massive particle. Okay, so I think I'm at 40 minutes, probably a little over. So I'll pause here. I'll pick up with this next problem. Okay, you can practice this problem with a proton in the meantime. I'll pick up with this problem, and then I'll deal with the potential energy of multiple point charges in a system. Okay, thanks. Again, any questions, let me know, send me an email. We can email, we can Zoom, whatever you want to do. Okay? Thanks. Have fun. See ya.